Okay. Ta-da. There we go. Alrighty. Let's go ahead and get started. Good morning, everybody. Welcome back. Today, we're going to continue talking about... Actually, let's see where we left off. I think we were talking about atoms. I think this will be your class here. Yes. So we were talking about all these bits here. Perfect. Okay. So let's do a couple more problems on that, where we are talking about the element symbols. So let's say that I have this much information. With this, can we go ahead and complete the element symbol and figure out the numbers of protons and electrons in here as well? Let's see if we can do that. So, what are we going to do? So we have two bits of information that we're starting with. We have P, 3 minus, and n equals 17. So that's what we know. How are we going to figure out the rest? Remember, an element symbol has got to have 4 parts technically. We have the number on the top left, which is our mass number. That's missing here. We are missing our atomic number down here. But we do have the symbol and the charge, so we have the rest of it. So we're only missing a few little bits here. So, let's see what we can do. So, we see that this is a P. So, probably the first thing we should do is try and figure out where that is on the periodic table, so we can determine how many protons this thing will have. And so, we'll go ahead and find it. Aha, here it is. It is right over here, phosphorus. So, periodic table says phosphorus has an atomic number of 15. Great, so we can use that. So, if we know our atomic number is 15, that tells us the number of protons, right? And so, we can now go ahead and fill a little bit more into our symbol, knowing we have 15 protons. Alright, we're still missing that light green though. And the light green was the mass number, right? Which is going to be the number of protons plus the number of neutrons. Now that we have the protons, we can go ahead and figure this out. We see, aha, it's 15 plus 17, which is 32. I hope, yes, 32. And so now we can go ahead and fill that one in. The last bit we have here is the charge. And so we see here, well, we don't know the number of electrons. That's the part we're missing. But we do have this charge bit that we haven't used yet. So let's go ahead and do it. We remember that the charge, let's do charge in light blue, is going to be the number of protons minus the number of electrons. And so we know that our charge is -3. That's part of our little phosphorus bit there. We see, aha, it's 15 minus whatever our electrons happen to be. If we add or subtract 15 from both sides, or rearrange this thing, we're going to see that we get 18 electrons here. We get negative E equals negative 18, and so therefore E is 18. So we will have figured out the number of electrons we have here. And we're done. We've solved it. So that's kind of that, I suppose. That's what we're going to be looking at in some of our homework, so I'll go ahead and post that for you guys so you can start taking a look at that. just working with the subatomic particles. And with that, we're pretty much done with atoms. So that's the end of chapter 3A. So short little chapter, or half a chapter, I guess. Although some of the A's and B's are really full chapters in themselves. So let's talk about compounds a bit. Did we talk about compounds actually at all last time? Let's find out real quick. I'll save this for now. Let's hop back to last time. I just see single elements here. Cool. Okay. Just single elements. Great. So we'll talk about compounds then. So compounds, as we might remember, these are more than one element. So things with more than one element that are compounds might look something like this, or that, or this, or something like that. Whatever. We have various elements combined with various other elements. And what's important here is that they have fixed ratios between them. We're going to see that every water molecule will have this ratio of hydrogen to oxygen. We're going to have 2 hydrogen atoms for every oxygen. There. And if you look at, say, this one, we have 6 carbons for every 12 hydrogens and 6 oxygens. So, we see that these have fixed ratios. So every single glucose molecule there, sorry, my allergies are like going crazy this morning too. And water, for example, has a 2-to-1 ratio of hydrogen to oxygen. These are fixed ratios. We see that compounds have fixed ratios of atoms. Alright, and that's how we can kind of help define them. So we know water is H2O. We're going to see every single water molecule is H2O, and so as a result we can say every single H2O is water. That'll work for most things, especially in this class. You get into later things though, you'll see, well, maybe not, like that C6H12O6, that's glucose, but it's also fructose and galactose and idose and glucose and 15 other sugars all have the same molecular formula. So little bit more complex. That goes into organic chemistry, so we're not going to have to worry about that. For us, H2O is water and HCl is salt, and we're good. Those are fixed ratios and they mean one thing. So we're good there. So with this in mind, we can work with these. We can say, well, no, we can't, not yet. We don't know enough yet. We're going to learn a way to determine the formula of a compound based on ratios of atoms later on. Once we talk about the next step, which is quantifying our atoms and compounds. So, any questions before we move on? Go to your spot. Okay. Alrighty, let's go for it then. So, unfortunately, atoms are very, very small, and we cannot measure them directly. They weigh incredibly tiny amounts, and so if we are to do any sort of like actual work with atoms, it's really impossible to isolate a single one, for any intents and purposes. And in fact, in order for us to even have a reasonable amount of material to work with, we need quintillions of atoms. And even so, it's like, okay, that's a relatively small amount still. So, we're going to have a definition here. We're going to see that we have a unit called the mole. Which is going to help bring things from atomic level, where it's very hard to distinguish, individual atoms, and bring it into real life scale, where we're talking about things where these units make sense. And we're going to see that the number of atoms that make a mole is about 10 to the 23rd power. We'll see, I have probably in my coffee cup here, I probably have 10 moles of water molecules. So 10 moles, a little bit easier to talk about, or I could say I have 10 to the 24th power water molecules in here. A little bit harder to use the 10 to the 24 because that's such a big number, right? 10 to the 24, let's write it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That's 23. Here's 24, because I have more than 2 moles in there. So nobody wants to say I have this many water molecules, right? Makes no sense. So we talk about moles instead, and we're going to see that moles will be a very useful way for us to talk about relating quantities to each other. This word, the mole, though, can be used for many things. We could say it about molecules. We could say 1 mole of puppies is same number, not molecules, puppies. A mole is just a word for this number of whatever we're counting. It can go with anything. It's like the word dozen. A dozen means 12, right? We could say 1 dozen atoms is 12 atoms. 1 dozen donuts equals 12 donuts. 1 dozen what shall we have now? Staplers, yes, of course. It's 12 staplers. It's really the same idea. So we have many words like this in English for some reason. I guess it's because people didn't know how to count very well, so that's where these words came from. But like 1 score, oops, that's a scone. 1 score, what do we use score for? We don't. Lincoln did. It's a word from back then because, again, people didn't really know how to count. But 1 score of years is 20 years. What other weird things do we have? 1 ream of paper is 500 pages. Ream is really kind of a specific one. 1 gross of, I don't know, of eggs is 144 eggs. These are all words that we have in English to describe numbers of things. We have one for 10,000 as well. 1 myriad. What would we have 10,000 of? Well, puppies, of course, right? So it's 10,000 puppies. So lots of words in English that work exactly the same way as mole does. Mole just happens to have a very big number associated with it. 1 Google, spelled like this, is 10 to the 100th power of whatever you're looking at. So if you're looking at 10 to the 100th jury duty summons, you could say you have a Google of jury duty summons. Whatever. All these can be applied to any, unit or thing we're counting. So the mole here is really the same idea. It's just a special number. We call that number, by the way, we have a name for it. It's abbreviated. It's capital N sub capital A. We call this Avogadro's number, after the scientist who worked with it, and that is this number here. So 1 mole of whatever is equal to Avogadro's number of that same thing. So of staplers, of students who pass chemistry, whatever. I mean, anything you can quantify, you can use a mole with it. Again, just a really big number, but it's an important one for us because scientists have determined. Actually, this used to be the definition of a mole, but things were changed recently slightly. But it turns out that 1 mole of carbon-12 atoms is exactly equal to 12 grams. I'm not going to say exactly because it's been slightly changed, so I'm just going to put 12.00. And we're going to see that this is going to be a very important relationship for us. So, this is the kind of bigger picture here. Because again, it doesn't really help us to count 10 to the 23rd atoms of carbon. But this is something we can weigh out. 12 grams. 12 grams of carbon is about a tablespoon of carbon. If you were to just say like powdered charcoal, like activated charcoal, I don't know, roughly about a tablespoon. So, something we can measure. And it turns out that Avogadro's number, same thing, is also, because that's 1 mole, is equal to 12 grams. Oops, there goes my phone. Oh well. So we're looking at here a very important relationship. This brings us from atomic level, because again, we have no way to count individual atoms. And so if we needed to count, again, a tablespoon of carbon, to count 10 to the 23rd power, it would take longer than the universe has been, alive. Not alive, but existent to count that. But this is something, we plop it on a scale, and we get our measurement in seconds. Milliseconds, whatever. Very easy for us to weigh out and, get our value out here. And we're going to see it's going to be very important because if we're talking about, say, water molecules, we can describe this as well. We can say, well, we know that if I have 1 mole of water molecules, that's Avogadro's number of molecules. I can say, okay, well, how many hydrogen atoms do I have in 1 mole of water? Mole is abbreviated MOL because why not? We'll just take the E off and now it's an abbreviation, but there it is. That's the abbreviation for mole. Well, we could say, okay, well, we know that one thing of water molecules is 6.022 times 10 to the 23 molecules of water. That's a conversion factor, by the way. Anytime we see an equal sign like that, that means something's a conversion factor. So we'll be using it like that. And so if we're asked how many hydrogen atoms are there in 1 mole of water, this is a unit conversion problem. Believe it or not, as I've told you, in chemistry, especially general chemistry, most questions are unit conversions. That's all they are. And so it's going to be very important that we really understand how to do that. So, what else do we know? Can we go directly from water molecules to hydrogen atoms? Yeah, right? We know from our formula of the chemical, we have 2 atoms of hydrogen for every 1 molecule of water. That's a ratio we have, which as a ratio is a conversion factor as well. And so we could say, okay, well, let's take a look at this. We have 1 mole, or here, let's even, we'll throw some Sig Figs on this too. Say 1 mole with some decimal points. If we have 1 mole of water, we're looking to end up in atoms of hydrogen. A couple of ways we can do this. But we see we have some conversion factors. We can make a unit plan. We're starting with moles of water. Well, if we look at the conversion factors we have here, we have a mole of water is 6.022 times 10 to the 23 molecules. So we can go from moles to molecules. Moles and molecules are not the same thing. Despite, unfortunately, they have very similar, in fact, the first 4 letters of molecule are mole, right? They are not related, unfortunately. We'll make that distinction in just a second here. I want to get through this problem and then we'll make that distinction. And then we have the second conversion here that tells us, we can go from molecules of water to atoms of hydrogen. So we can do that here. And so that's our plan. We'll go from moles to molecules, from molecules to atoms. So let's go ahead and do this. So we have 1 mole of water. If we are going to apply our conversion factors, if we want to go from moles to molecules, we have that. Remember, we have moles, so we want to cancel out moles. So we're going to put moles on the bottom. Since we are having different substances here, it's a good idea to keep your what that is. That's why I'm going to put water each time here, because we're looking to get hydrogen at the end, which is not the same thing. So it's important that we keep track of what's what. Well, we know we have Avogadro's number of molecules. I'm going to just put H2O there because I'm already out of space. And then we have another one. We know we have 2 atoms of hydrogen for every 1 molecule of water. Notice moles of water cancel out. Molecules of water cancel out. We're left with atoms of hydrogen. And so we can go ahead and do this calculation. So if we do that, it's really just 6.022 times 10 to the 23 times 2. So let's do it. 6.022. Where is my EE button? There it is. 23 times 2. And we get 1.2 0.20 times 10 to the 24th power. I've left it as 3 sig figs because we've started with 3 sig figs. Remember, we're always going to kind of look at our starting number to make that determination. So we've calculated now how many atoms of hydrogen we had in this water sample, which was 1 mole. So there we have it. We have calculated our number of atoms. All right, so it's just the same idea here, unit conversion. That's all we have. So one thing that students do tend to confuse moles are not the same thing as molecules. A mole is a number, like a dozen. So it's just a way of saying a number but using a word instead. Molecules are specifically, I'll give you a more specific definition than I want to. There's a hair on my tablet. Go away. Molecules are compounds containing only nonmetals, but we'll talk about that later. We'll learn about what nonmetals are later on, but suffice it to say they are a type of compound. So a number, like a dozen, is not the same thing as a compound, right? They have nothing to do with each other. One is a number, one is a way of counting like one unit of a substance. So we have one water molecule that is here, H2O. We can have 3 of them. Now I have 3 water molecules, so each of those is a molecule. A mole is a number, so that is just saying 6.022 times 10 to the 23 of whatever. So we can use it for atoms, we can use it for molecules, we can use it for puppies, we can use it for jury duty summons. So whatever. Number of somethings. Molecule is a compound. One entity of that compound. So one water molecule. All right, just so we're clear, I say molecules here because that's compound. When I say atoms, that's just one of an individual element. So that's why I said how many hydrogen atoms are in our water molecules. Water is a compound. I was looking for hydrogen atoms, which are individual one element. Within the compound or without, it doesn't matter. I'm just looking at that particular element. So one water molecule is made of 3 total atoms. We have 2 atoms of hydrogen, 1 atom of oxygen. So I'm just going to write that out so we're super clear. One water molecule has 2 atoms of hydrogen and 1 atom of oxygen. So the atoms are the individual elements, like the little individual atoms there. The oxygen is also 1 atom. It's an oxygen atom. It's a different type of atom, but they're atoms nonetheless. And a molecule is the combination of the 3 of those. So, people sometimes draw it, let's see, with green. We'll draw a water molecule kind of like this. The hydrogens are the small little bits there. We'll talk about atomic size and all that later on. And the oxygen's the middle there. So that's a molecule. The whole thing is the molecule. These are the atoms. So 3 things put together for this makes a molecule. each of those things are atoms. All right, so that's the distinction we use here. And again, moles are just a way of counting things. So if I said a dozen water molecules, that's analogous to saying a mole of water molecules. It's just a different number. That's all it is. So nothing terribly scary there. So, any questions so far? You guys are rocking it, perhaps. Or perhaps everybody is still asleep. Which is, I guess, fine because you can just watch this later. So, hooray. Alrighty. Cool. So, actually, how many viewers do we have? Let's see. Well, we'll find that out later. Cool. Let's go ahead and move on then. So, with this idea, kind of the idea of with that idea of having the 12 carbon-12 atoms being equal to 12 grams of carbon-12 atoms, we're going to see that we're going to have something called molar mass. And molar mass is going to be the mass in grams of 1 mole of a substance. So if that's substances atoms, or if it's molecules, or whatever substance we're looking at, we're going to see that we can use this idea of molar mass to get those equal to each other. And so the molar mass is actually something we've kind of seen before. For atoms, the molar mass is equal to the atomic mass. So if I were to say, okay, what's 1 mole of oxygen atoms, you could say, aha, that's equal to 16 grams of oxygen. How do I get 16? Periodic table, which I've just closed. Okay, let's try that again. And in fact, I've probably just closed my notes. Oh well. Oh good, it's saved. Oh thank goodness. Okay, where were we? Oxygen. If we click oxygen, that's where I got the 16 from. Apparently this particular periodic table uses 15.999. Your periodic table will use whatever it uses, right? I usually use 16.00 for oxygen because I don't need all those extra decimals. Sorry, now I have to kind of scroll back to the bottom here. So that's where I got that number. If I were to say, okay, how about if I have 1 mole of, I don't know, what's our next favorite element? How about the xenon atoms? Well, that one I don't have memorized, so we'll go and find xenon on the periodic table. Aha, it's on the right, number 54 there. I'm going to click it, and we see we have 131.29, we'll say. 131.29 grams of xenon. So, this is going to be a very important number for us, because, remember 1 mole, just the number. So, that tells us that we have a very important conversion factor here. That number of xenon atoms is equal to the atomic mass of xenon. So, very, very important relationship, one that we're going to be using all of the time in chemistry. More often than not, we're going to be using this version because nobody likes to write out all these exponents. But for right now, it's very important that we do so that we fully understand kind of the magnitude of why we need a better unit than just atoms when we talk about moles instead. It's going to be a little bit easier for us when we use moles. Alright, so that's for atoms. Individual atoms we can talk about using their atomic mass. For molecules, or compounds, we'll say, the molar mass is the sum we're going to see it's the sum of the mass of all the elements in the compound. So, for example, for water, that's a compound. If we want to find the molar mass of water, that's going to be the sum of the atomic masses of all the elements in there. So, we're going to need to do the mass of 2 hydrogens plus 1 oxygen. If we bust out our periodic table, we see that hydrogen is 1.008 and oxygen is 16. And we'll get about 18.02 there. That's rounded. I typically round this number. People always ask about Sig Figs for these, for molar mass. Don't worry about it, because these, unfortunately, our periodic tables they can give us different numbers, just depending on how many Sig Figs they have. So we're not going to worry about the Sig Figs. These aren't measurements anyway, so they're not going to have significant figures. We're going to be using molar mass as a conversion factor anyway, so again, we're not going to worry about Sig Figs for molar mass. Typically, just use 2 decimal points. So 18.02. If you want to say 18.016, go right ahead. I will not stop you. That is just fine. But that is the molar mass of water, 18.02, which tells us that 18.02 grams of water is 1 mole of water molecules. So 18 grams, not very much. When you're, let's see, what's a way you might know this? Think of a soda can, right? A can of Coke has 32 grams of sugar in there, something like that. And so it's, 32 grams is not a whole lot. Consider that about 15 grams of water is a tablespoon. So we're looking at just over a tablespoon of water is 6 times 10 to the 23rd power molecules of water. So you have quintillions of water molecules in your tablespoon of water. So tons. All right, how about for something like CO2, carbon dioxide? Well, we'll say that we need to add 1 carbon plus 2 oxygens. Looking on the periodic table, we see carbon, 12.01, plus 2 times 16 is going to be 44.01. That's the molar mass of carbon dioxide. So we're going to see that carbon dioxide, we're going to need about 1/3 as much carbon dioxide as we would water for it to weigh the same. That's not about 1/3, but close enough. So we'll see here that, the bigger your molecule is, it's going to weigh more. And it's going to have, you're going to need a bigger mass of it to get the same number of molecules or atoms or whatever you're looking at. How about another one? Formaldehyde. For this, we would add up 1 carbon plus 2 hydrogens plus 1 oxygen, 12.01 plus 2 times 1.008. Again, these numbers are from the periodic table. We do that, we get 28 plus 2, 30 point... Oh goodness, okay. I'm going to have to bust it out. Calculator. 12.01 plus 2 times 1.008 plus 16. 30.17 is what I get apparently. Oh, I put 1.08. Ugh. Hold on. I was going to say that number is a little bit high. Plus 2 times 1.008. There we go. Yeah, that's more like it. So, 30.03. So, there we have it. That would be our molar mass of formaldehyde. So, again, these numbers are the atomic masses and those are from the periodic table. So I do suggest you find a periodic table you like. If you Google periodic table, you're going to get 80 cajillion versions of it. Find one you like, print it out, or save it somewhere. And you'll want to just, it's best to just be consistent with your periodic table. So, because we're going to be working with it a lot. So, get familiar with it. Use whatever numbers it provides you. If yours gives you 15.999 and you want to use that, go ahead for oxygen. You're going to get relatively the same answers. So I'm not going to really judge you on that. So use whichever periodic table you like. So, cool. All right. So, molar mass. Again, all of this tells us 3 things. We know that 1 mole of formaldehyde molecules is 30.03 grams formaldehyde. I'm sorry, I'll just say H2O. That's the most useful conversion factor we get out of this. Because now we can bridge the gap between atomic level things that we cannot count very easily or measure very easily to something we can measure very easily. And we're going to see later on when we talk about chemical reactions, just like how compounds have fixed ratios, like water has 2 hydrogens and 1 oxygen, chemical reactions are going to come in fixed ratios too. And so instead of saying, okay, well, 1 molecule of sugar is going to react with 1 molecule of oxygen, and now we have, 6 molecules of oxygen. Now we get 6 molecules of CO2 and 6 molecules of water. Those are all fixed ratios. And it's silly for us to talk about molecules again because we can't really count those. But moles is something we can kind of easily conceptualize. We can say, well, the ratio is 6:1, so we'll see that later on. And these ratios are going to be useful for us to kind of now go into things we can use, which is mass. So we'll see that those ratios are more important, but bringing them into the mass type of idea lets us actually work with them. So let's go ahead and put those there as well. So we know that 1 mole of formaldehyde molecules is 6.022 times 10 to the 23rd molecules. And since those two are both equal to each other, if we really wanted, we could say that it's equal to Avogadro's number as well. So since the first two both had moles of H2O, we can equate the last 2 bits there. So we get 3 conversion factors out of this. And we're going to get 3 conversion factors for any substance. We would say it's molar mass in place of these things. So everything else here stays the same except for this number. This number just changes with your compound, or if you're looking at atoms. The rest of the stuff stays the same. So remember, this is the molar mass. And so that depends on the compound. Or let's say on your substance. Because you could be looking at atoms too. Okay, so with that in mind, let's work with it. Alrighty, so I've got 500 grams of water. That is one little water bottle, 500 mLs. For water, grams and mLs are the same. So I've got my water bottle. It's just a small water bottle, it's not even the big one. Let's see how many molecules are in that, using this idea. So, keeping in mind this is for formaldehyde, but the same equalities are true for water, we would just need its molar mass instead. So, if we're looking to go from grams to molecules, that's just one conversion. We see here on, at least the ones for formaldehyde, we see that one of these conversion factors will get us directly from grams to molecules. And so that's going to be the third conversion factor, right? Although in this case it's got the molar mass of formaldehyde. We have the molar mass of water. We calculated earlier. It's 18.02. So we can say, that's right. 18.02 grams of water is equal to Avogadro's number of water molecules. Great. So we can just go ahead and use it. So 500 grams. We're going to put grams on the bottom so they cancel out. Remember, grams over grams is 1. They cancel out. And we're going to put our Avogadro's number, therefore, on the top. And doing this, 500 divided by 18.02 times 6.022 times 10 to the 23rd. And lo and behold, we get 1.67. Looks like we need 4 Sig Figs here. 1 times 10 to the 25th power molecules. Again, if we really wanted 1671, so that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Who is going to count that many molecules? In one bottle of water. That's all it is. That's how many water molecules you have in one bottle of water. The 500 ml bottle, half a liter. 2 cups, you can say, is about that many water molecules. So, kind of impossible to count. But we're going to see we need some way to do it. And this is very easy to count, or to measure. Very easy to measure. But we're going to see that we need to know the number of molecules sometimes. And so it's very important for us that we understand how to do this. Again, just converting. Grams of water cancels, we're left with molecules. That's it. Just unit conversion. All right? Wow your friends. Say, look at this number here we've done. That's how many water molecules are in my bottle of water. All right? Let's take a look at another one. What shall we do this time? What is the mass in grams of one, what shall we say, lead atom? Let's see how much one atom weighs. As always, this is a unit conversion, trust me. We're going from atoms of lead to grams of lead. PB is lead. Comes from Latin plumum. And so, or is it Greek? One of the two. And so that's where the letters PB come from. That means lead, though. It's one of our elements. So we just need to find our conversion factor between these. And that conversion factor is the atomic mass. So let's find it out. Let's find out lead's atomic mass. Lead is number 82. Here it is. 207.2 is our atomic mass. So here we go. We know our conversion factor. We have Avogadro's number. Was it 207.2 grams of lead. So we always will start our conversion with what we do know. We have one lead atom. That's what we're going to start with. That's the number we have. And so one lead atom, the Sig Figs are exact. Okay, we're not going to worry about Sig Figs for this one. Because this calculation is kind of, there's no way for us to prove it because the mass we're going to get is so small. But anyways, one lead atom. We're going to need to put atoms below. Atoms of lead on the bottom. Because we need atoms to cancel out. We need this to go away. We don't want that unit anymore. We want to have grams. And so 207.2 divided by 6.022 times 10 to the 23rd. You should get, I'm going to just put 3 Sig Figs. Sorry. I know this problem shouldn't have Sig Figs. It should have 1. But we're not going to worry about that. Since we can't have 1.02 lead atoms or something like that, doesn't make sense. But we'll just keep this as is for this problem. So 10 to the negative 22nd power grams. So our most expensive scales, balances, things that measure mass, can go to maybe 0.001 milligrams. No way at all for us to even get close to being able to measure this. So that's not even close to micrograms, not even nanograms, picograms. We're still, tiny fraction here. So this number here is impossible for us to verify. We can't just take one lead atom because we can't count one lead atom out. And so measuring that mass is impossible, but there you go. Wow, your friends, that's how much an atom weighs. A very, very small amount. Right, of lead. Other atoms would weigh different amounts, but that's the mass of one lead atom. All right, again with 3 Sig Figs for no reason. But there it is. All right. All these very exciting calculations, I know. Let's take it up a notch. How many oxygen atoms in 100 grams of CO2? That's a G. Let me change this question because we've been doing a lot of grams to atoms. I want to do something different. Moles of oxygen atoms. So how many moles of oxygen in 100 grams of CO2? Well, let's see what we can do here. Well, we know, if nothing else, we know that we have a conversion factor between grams and moles. We can go of the same substance. We know we have molar mass, which will get us between grams and moles, or grams and molecules if we wanted, but since I'm asking for moles, we don't need to worry about molecules. We have a conversion, remember, directly from, we've been using conversion factor 3 here, grams to molecules, or grams to atoms, whichever one. But now that I want moles, we'll use the first conversion factor, moles to grams. We don't have to worry about molecules. So, we can do that, but how are we going to go from moles of CO2 to moles of oxygen? Well, there's a couple ways we could do this, but you can do it in just one step if you wanted. You can go directly to moles of oxygen atoms. I'll write moles here. We know that there's 1 or 2 atoms of oxygen for every 1 molecule of CO2. We have that. That we know from the chemical formula. We also can tell, well, if I had, why don't I just multiply this equality by something? I can say I have 2 dozen atoms of oxygen for 1 dozen of carbon dioxide molecules. That's true. Every CO2 has 2 oxygens. So if I have 12 CO2s, I'm going to have 24 oxygens. So, it's completely reasonable to say the same thing with moles. I can say this equality too. For every mole of carbon dioxide I have 2 moles of oxygen atoms. So, again, might seem scary, but honestly, it's exactly the same as dozen. It's just a more complicated number. That's it. But it's just a number. Nothing scary about a number. Let's go ahead and do this problem then. So, we're going to need 2 conversion factors, right? This conversion factor here is our molar mass to go from grams to moles. And then from moles to moles, well, they're of different substances, but we know that it's this kind of, this bit. That's the equality we're going to use for this conversion here. Now, do we see where we got that last conversion from? The one in green. So just taking things one step further. And don't you worry, this may seem complicated now. It will very soon become secondhand to you, second nature. So you'll be doing this in your sleep. Don't you worry. Okay, let's do it. Starting with the number that we know, which is 100 grams. That's the number that we're starting with because that's the number we're given. We have written out in our plan, we're going to use the molar mass first. Fortunately, we've calculated that somewhere up here. For CO2, it's 44.01. Am I going to put it up here? Not going to put it there. The reason for that, if we just do this, we'll get 4401 grams squared over mole. The hell unit is that? Right? Grams times grams is grams squared divided by moles, which is a nonsense unit. So just remember, even if you completely forget how to set things up for dimensional analysis for unit conversion, just look at the units. See, if you are multiplying them, you're going to end up squaring or whatever your unit, and you need to make sure things cancel out instead of squaring things. So that's not a good idea. So indeed, we're going to put the grams on the bottom because grams over grams times moles is just moles, right? Grams over grams is 1. So we're going to put grams on the bottom so that they cancel out. And then we have 1 mole CO2. Again here, this is our molar mass. All right. And our next conversion factor, we're going to use moles of oxygen and moles of CO2. Am I going to put it this way? If we do this, we end up with moles squared of CO2 over moles of oxygen. Is that what we want? Nope. That's, again, a unit that makes no sense. So we're going to not have that. So it's also very important that we keep track of which is which. So that's why I'm very clearly writing CO2 for quantities that belong to CO2 and oxygen for things that belong to oxygen. So you can't just say, well, these should cancel, right? No, they're of different things, so they can't cancel. So that means I've put this upside down again. And so let's now double check that everything is correct here. Do we have grams of CO2 in the numerator and denominator? We do. Grams of CO2 can cancel out. Do we have moles of CO2 in the numerator and the denominator? We do. Those can cancel out as well. And we're left with moles of oxygen, which was the units that we wanted. So let's go ahead and do this. 100 divided by 44.01 times 2 is equal to 4.544 moles of oxygen atoms. And that's our answer. If we really wanted, we could see the exact number of oxygen atoms, but we're going to see it's a little bit easier for us to talk about moles. Here, I'll go ahead and do the calculation for atoms. 4.544 moles of oxygen, or we could say 2.737 times 10 to the 24th atoms of oxygen. These things are the same thing. If we want to think about which number is easier to talk about, here, let me get rid of the word or there. These mean the same thing. If we really wanted, we could talk about atoms, individual atoms or individual molecules for the entire course. But if you had a choice of which of these numbers you'd rather do math with, I believe most of you would choose the one on the left. It's a lot easier to put in our calculator. We can even, do some more like mental math with it. So we're going to see that using moles is a lot easier than using atoms directly, even though these two do mean the same thing. How to get between them, by the way, I just multiplied by Avogadro's number, but that's how I got that number. But we're going to see here that these mean exactly the same thing, so it's easier for us to say the left number, the 4.544 moles. It's a lot easier than saying 2.737 times 10 to the 24, and God forbid if you write out that whole number. Don't do it. Don't write it out. Remember we did that with the 25? If you really want me to do that, I'm going to just say, no, you're wrong. Because I don't want to read that many zeros and count them all. So, don't. Moles are our friends because they're going to make things easier to talk about. Alrighty, any questions so far on this? How we got our moles of oxygen out of this? We can kind of now talk about them, some applications of this. So rather than just say, okay, we can do all these calculations all we want, but what's the point? I'll give you one. We can talk about something called mass percent. Which is the mass of one element in a compound over the mass of the compound. Since it's a percent, we can throw that on there as well. And this is very useful because, say, you have a patient with hypertension, has been asked by the doctor, or you're the doctor, to advise them on to put them on a low sodium diet, right? And your patient is like, okay, well, 1 teaspoon of salt is 1 teaspoon of sodium, and whatever mass that is, that's going to be over their daily limit or whatever. But you'll be like, wait a second, salt is actually sodium chloride. It's not sodium by itself. So we're going to see that there's a way to tell how much sodium is present in a sample of salt. Because salt is a compound, sodium is one element within that compound. And that's the element we're interested in. We don't really care how much chloride the patient is getting, because we don't really have a dietary limit on the amount of chloride we can have. So let's see what this looks like. Let's do it for sodium chloride. So if we wanted to do this, we could say the mass of one element in a compound over the entire mass of the compound. And it's easier here if we just talk about molar masses. Since we don't have exact masses, we're not going to go ahead in the lab and figure out how much sodium we have versus how much sodium chloride we have. It's easier to just use the molar masses. So we can go ahead and say that. So since these are just, since the top one is just going to be sodium, we can say, aha, well this is going to be the mass, or molar mass, of Na over the molar mass of NaCl. Is 100%. If we do this, again, we're going to look at our periodic table. We're going to find the elements and we're going to add them up. I happen to have these two memorized, so we're going to just copy that. Again, these numbers are from the periodic table. Let's just do it. Why not? If we are to look at sodium, it is here on the left, number 11. We get 22.99. Or if you really want, use all of those numbers. That's fine, go ahead. Chlorine on the right side here. Right here, number 17. 35.45. That's where those numbers have come from. Notice, by the way, the units it gives us are grams per mole. So we've already got our kind of molar mass unit there. But I'm going to just leave them as grams for now. So we can do this. I often will forget this times percent on it, but you're going to get a decimal. Just convert it to a percent. It's not bad. Let's do the math. Here we go. 22.99 divided by parenthesis 22.99 plus 35.45, close parenthesis. And I get 39 point, let's say 34%. I'm going to just use two decimal points just like before. Again, these aren't measurements, so we don't really have Sig Figs with them. So I'm just going to go ahead and give 2 decimal points. So we can say this compound is about 39% sodium by mass. So if you're saying this patient should be limited to 2 grams of sodium per day, I don't know if that's a high number or I don't know. I don't actually. I'm just making this up as I go. So if the patient is limited to 2 grams of sodium per day, how many grams of NaCl can they have? We can use this mass percent idea to figure it out. We know that of our sample of sodium chloride, about 39% of it will be sodium. So if we want to end up with 2 grams of sodium, times some mass of sodium chloride, right? Remember that percents are really decimals. We can say, okay, instead of writing it that way, it's mathematically better to, if we're going to actually work with this number, to keep it as the decimal form. And so we can say, okay, well, you know, that we're going to get, 2 grams divided by 0.3934 with no unit. Percents do not have units. 2 divided by, I'm just going to put the answer, not natural log. How did we get there? Delete. Okay. Doing that, we get 5.08 grams. Grams stays there. That's the unit we had before. And so we get this. So we can use this mass percent idea to say, okay, well, patient, keep yourself to 5 grams of sodium chloride, of salt, and that way you won't exceed 2 grams of sodium per day. So you can say that. So that's the utility of the mass percent idea. All right, so we can go ahead and work with that. All right, any questions on that one or any of the others we've done? So when I'm planning these lessons, by the way, I do usually put like around 15 minutes of question time in here. So I guess if we're not having questions, we're going to get out a little bit early each time, which is cool, whatevs. With this, though, let's kind of just, if you're interested in reading ahead, what we're covering next time, we're going to do the opposite thing. We're going to use mass percent to determine what's called an empirical formula. How are we going to use, we can use masses of elements to determine what the formula of a compound is, which we call an empirical formula. What else are we going to do next time? We can talk more about moles. Our favorite. And if we finish all of that, we're going to then start talking about electrons and how they behave within an atom. Let me actually check something here. Let me look at our syllabus real quick, because this is the end of the 3rd week. I'm just going to check when our first exam is, so we are prepared for that. What class is a C101? There it is. There's the syllabus. This is for the wrong semester. Okay, let's try again. F21, C101. There it is. Okay. So our first exam, apparently we're having on Monday. Exciting. So it's going to actually cover... It's a good thing I checked this, right? Let's move that away. Let's talk about your exam briefly. Your exam is on September 13th. That is a Monday. We're looking at around 30 questions or so. It's multiple choice on Canvas. So on Canvas, on Monday, you will log on anytime you want. It is open from 12 a.m. midnight to 11:59 p.m. So you have 24 hours on Monday to take this exam. I think the time limit is going to be probably about an hour. This exam is a little shorter because we haven't really covered much, right? Let's move this guy down a little bit. Again. All right, plan for around 1 hour or so. First exam typically does not take that long because it's, again, the first one. So plan for about an hour on it. I might change that. I might give you a little more time. We'll see. But plan for about an hour or so. It's, again, open book. I have no way of stopping you, so go ahead, use whatever notes you want. But not open friend. I do have ways to investigate these things, so best not to do that. But yeah, go ahead and use the internet, use your notes, use your book, have fun doing whatever you want. Just be aware, because it is timed. All of those things, every time you're looking at your notes, you're looking in the book, you're looking online, that's eating up your time. So, chances are when people say, well, we didn't have enough time with this exam, you do if you're prepared. If you are spending, 3 minutes per question looking things up in your notes, you're going to end up not finishing in time, right? Because that would take you 90 minutes to do, if that's the case. So just keep that in mind. The more prepared you are, the faster you're going to be able to work. So we'll go from there. Everything so far in the course is fair game. So I can put anything I want from our first 3 kind of chapters here. So I'm not going to put stuff probably from today on it, because I realize you have then 4 days only to ask questions and all that. So probably we'll have it go through Monday. Or I'm sorry, what Tuesday's class. So probably 2 about there. So stuff about dimensional analysis, unit conversion, Sig Figs, atoms, matter, that sort of thing. So everything we've covered up until today, basically. So I'm not going to probably throw the moles at you quite yet. I might ask you to calculate molar mass, because that's relatively easy. But I understand that a lot of you are going to need a little bit more time to process the unit conversions of moles, so I won't throw that at you. All right. What else can I do? I'll put some. I think I have practice exams on Canvas for you guys, so you can use those. I can't remember if those ones are multiple choice or not. In either case, they're going to be useful for you. I have the keys up for those as well, so you'll be able to use those. So those are on Canvas. So if we pop over here, let's see if I am... Okay. Let me share this screen. 1 sec. So... Yes, I do have exams here. Okay, so if we go to Canvas, let me share my that screen real quick. There we go. At the very bottom of our home page, I have practice exams. I will have, since your homework is due today, I will have the homework keys for those activities. I'll put a few more. You'll have a few more homework assignments that'll become active. I can activate them right now, in fact. None of this extra practice is relevant right now, but if you go all the way to the bottom, you'll see our practice exams. Soon you'll have access to the homework keys, so you'll want to make sure that you compare your answers that you submit on your homework with those of the key. So remember, how I grade is I can't give direct feedback because I have 120 of you all submitting 2 assignments per week. When I'm grading things, I can't type out, well, on number 1 you really should have decided to put this number instead. And no, unfortunately, it just takes too much time to do that. If this were a real class, I could, circle things and be like, wrong molar mass or something. And unfortunately, it's just not possible with online. So just letting you know there. So it's up to you to check your own work against the answer key. How I grade it is I do look at a couple problems in depth, and the rest I grade on completion. So so even if you get 100% on your work, that doesn't necessarily mean you got everything exactly right. So you'll still want to check the answer keys. So the answer keys will become available. I'll probably make those available to you probably Saturday. Let's see, I can probably set that, whatever. We'll deal with that. I'm going to give you, they are due tonight, your homeworks, right? They're due today. But I always give a little bit of leeway in case people are turning things in late, because remember, as soon as I post the key, no more late work can be submitted. So I'll make that probably available Sunday or Saturday at midnight. So you'll be able to look on it over the weekend so you can see the keys. Okay, if you do have questions, I think you have labs due as well this weekend, yeah. So I'll have those. And yeah, we'll go through with that. So, cool. I'm going to go back to myself here. Great. If you do have questions, put them in Discord, and we'll go from there. So, with that, enjoy the rest of your day. Enjoy your weekend. Study well. If you see people posting on Discord about the exam, tell them to look at today's video at the end or today's notes so they can kind of see that. So, and again, I'm going to say this. Remember, the exam dates are all on your syllabus. We went over those on the first, in fact, before classes began. And so you are expected to remember those. So I'm not going to send out like announcements, hey, don't forget you have an exam today. So hopefully everyone watching this later understands that. So, all right, cool. Very good. So your exam will be at the very top of the homepage on Canvas on Monday, and you'll have fun with it. So, great. Alrighty. Enjoy your weekend. Take care.